brush over the idea of neural network is we were saying that, okay, human brain is basically able to receive all this complex data and in a moment, for example, quickly make a decision and solve a complex, basically, problem, right? The idea was, okay, how could we come up with a model that could have such potential power, basically, could we mimic, the human brain, that could we have a hypothesis, basically, that receives all sorts of data and could, solve the problem, like image, audio, sounds. Like, for example, if you think about the humans, how could we, you listen to a start of a sound, quickly who's the singer, right? So it's like how your brain can make basically such a complex decision. Or you're looking at an image, this image could be full of difficult, basically, patterns or difficult objects in it, but you can quickly describe what you see in it. You can say what's in that image, right? In general, the human brains were really good for unstructured type of data. Unstructured means anything that's not in a tabular form, like audio. So basically, audio, videos, image, text. So anytime that we deal with this type of data, unstructured, human brain is really powerful. And that's why actually, if you want to create a model that works over unstructured data, we always need to have some sort of baseline, right? So to see that, imagine I develop a model and I want to sell this model, and I need to prove this model is good, right? So if we work with unstructured data, we try to compare it with human level performance. It's called HLP. Because we know human brain is really good for unstructured data. So the baseline is one of the baselines is like basically HLP. So you hire series of domain experts and you give them a data, either the same data or different subset of data, and you ask them to, hey, listen to this song or look at this video and give me your answer. And then you average the results among those, and that becomes the HLP, human level performance. So the neural network, for example, that you develop, should be, if not better than that, it should be in the same level as basically HLP. But when it comes to tabular data, a data that is like a CSV, for example, format, right? Then our brain is not that good. Because when you're looking at this tabular data, think about it. If I put a table in front of you, what could you tell me? Nothing. You're like, I don't know, it's just some bunch of numbers and stuff like that, right? Even if you see categorical columns that they have a meaning, right? You cannot infer anything from it. Like, for example, if you ask everyone in this room, if I ask each of you that recommend me a restaurant, you all need to give me a different answer, right? We are not really good for making decisions around when it comes on structured data, but we are really good with unstructured data. Now, the idea was that how could we mimic this, this complex system as convert it to some sort of model that could help us solve difficult problems. So, neural basically we are trying to map x to y using a series of non-linear functions. It's possible, to have a neural network that you have also linear functions, but we normally force it to be non-linear function because we want to learn complex problems, complex patterns. If it's just linear, you just learn linear, basically domain, right? Now, the building block of a neural network is called a neuron, right? Which the idea is that, it's like the neuron in human brain. And we have seen something like this is in SOM, right? Self-organizing map. Those processing unit, those are almost the same thing as it is in like a neuron. Now, every neuron, we're going to define it in this form. Basically, imagine this is a neuron. Neuron has, we're going to say it has two parts. There is an input to a neuron. There is an output from a neuron, okay? and then there is a Z and A. Okay, so every neuron has a Z, which is the basically input, basically technically is the weighted sum of or raw input to the neuron. That's Z, and has an A. A is that it's called activation map. It's actually that nonlinear function. That is A. Okay, and it has an output basically. Right? Now, input to neuron, this arrow, that doesn't mean that it's only one input. It actually could be series of arrows goes to a neuron, right? It's just we will start with that, then we will expand it. But in general, a neuron will receive an input, process that input as a weighted sum. So Z, it's simply basically a weighted sum. Yeah. So, well, we can just say that, yeah, xi is part of this input. Imagine input basically, let's write it here. So input to a neuron, if we have xi has d dimension, right? Your data set has, for example, d columns. So that's input. So that means that technically these are d, actually, let me draw it somewhere else. So technically, you have x1, x2, all the way to xd. D arrows goes to that basically neuron, right? And here you normally have also +1, which is a bias term. Okay, so neuron has series of arrows that goes to neuron. Those arrows carry the data. They are either coming from the input or come from different neurons. And then there is a +1, which stands for bias term, basically. Okay. Now, Z, which is the Z, is simply weighted sum of these arrows plus the bias term. Okay. Now, these weights and bias are what we need to learn in order to have the neural network. We don't have it, we want to learn it, right? So, and every arrow has basically has an input data, and it also has a weight. Okay, so we're going to fix the indices for this later, but this is basically a simple case here, right? So if you just make a lame example. If you want to think about these arrows, think about them as a pipe, okay? And whatever goes through the pipe is the data, and the length of the pipe, it's going to be the width of the pipe is going to be the weight. Right? The larger that weight, the more data goes through. The smaller the weight, because you do a multiplication, so the data becomes smaller, right? So that's could be some analogy. And then we have A. A is an activation function. Okay, so when you are saying that A is an activation function, so A is simply a function, some function over Z. Okay, so Z is the raw input to the neuron, and A is simply a function that gets whatever is Z and then gives you another number, gives you a scalar. Okay, so basically it's an R to R function. Now, the idea behind this activation function is that we want every neurons to learn something different, basically, or we want these neurons to learn something different about the data and learn more complex patterns. So there are a series of activation functions that are already out there that you can basically use. For example, we already have seen sigmoid, right? Sigmoid is an activation function. We know sigmoid of Z basically, it forces the value to range 0 and 1. Is there like a probability value? We know it as the following form. You know, the derivation of sigmoid basically is sigmoid times 1 minus sigmoid, right? Then you already have seen softmax, which basically is which it's if you have multi-class, basically we have tan tangent hyperbolic tangent function, or tan h, which basically over z is e to the power of plus z minus e to the power of minus z. So tan h forces the value to the range -1 and +1. The derivation of tan h was 1 minus tan h to the power of 2. And then there is another one, let's write it, ReLU, or rectified linear unit, okay, which is maximum of 0 and z. There's a function that whatever z is, if z is negative, will always return 0. If it's positive, will return z. And it basically looks like this. On negative is always 0, and on positive is just z value. Okay. The derivation of this one is also +1 if z is positive. If z is negative, is 0 and is undefined. Undefined if z is equal to 0. Now, there are lots of activation functions currently out there. So this is just some example of this activation function. You can always, whatever platform you're using, TensorFlow, PyTorch, they always just go to the website and you see a list of all the activation functions. But what you want to focus is that the benefits of these activation functions, and basically the pros and the cons, to have some sense of those when you want to use it in your application. To know, for example, if you want to use NLP versus if you want to do image processing, do a search. They already have done some researchers who came up that maybe this one is better for NLP, this one is better for example, images. So have some idea, but also I understand the range of values that they are producing. Okay. Now, sigmoid by default had when your neural network is larger, sigmoid tends to have a problem. It's called gradient vanishing. The gradients of the we have seen this gradient before. In neural network also works the same thing. We are going to work with gradients. If your network is large and you have been using sigmoid, what happens is that the larger the network, the gradient goes towards 0 and vanishes basically. If the gradient is 0, it doesn't matter how many times you iterate, you are not updating any W's, right? So the reason, because of that gradient vanishing, for example, we came up with tan h, which technically does the same thing, it just increases the dynamic range rather than 0 to 1 to -1 and 1. So the range is larger, so you don't have that problem with gradient vanishing. Okay, so it's really common these days to work with tan h and ReLU in deep learning fields. Okay, so those are one of the two well accepted, commonly used out there. But again, anytime you want to use it, it's kind of like a try and error. Try tan h, run it once, try ReLU. It's like try different combinations, and then pick the one that's more useful for you. Now, all of these activation functions, they are the one that at least we have here. They are responsible to learn some sort of nonlinearity from the z value that we are passing. Z simply is a weighted sum, is a linear value. Right? So it's a linear data. So we did weighted sum of the inputs plus the bias. Then you pass that to A and say the A job is to basically either squeeze the range of Z or basically learn some nonlinearity over that. Right? And then pass that value out. Okay, so output is when we say output, This is the same as A, basically. Whatever this A will produce, that becomes the output of the neuron. Okay. So now, so that was the building. That was the definition of the building blocks of neural network. This was the activation function. Now let's see what is an basically general neural network. So neural network, the idea is that you bring those neurons that we define and stack them on top of each other, right? So when you basically stack up neurons on top of each other, it's called a layer. A layer in neural network, when you hear a layer, like my model has 10 layers, each layer is technically a stack of neurons on top of each other. Okay. And each neuron has the following form. Okay. So each neuron has an input, raw input Z, and A as activated value. Now, if you put series of these layers after each other, basically, even one layer is the same. You could have from one layer to whatever number of layers. That becomes basically a neural network. Actually, you're creating a networks of neurons, basically. Right? So you will basically have, let's say, we can make it smaller so I don't need to make too many connections. So you have the first layer, which is called input layer. So input layer, it's simply the input data that you have, xi. So if xi has d dimension, you need to put d neurons in it. Each neuron represents one of the columns that you have, right? We call it, rather than input, we call it input layer, because if you write it as a layer for your network, you can basically, combine it together. It's much more efficient for computation. And so we just basically have it as a layer. We add it to the network, and we call it input layer. Then the last one is called output layer, which is the last layer of your neural network. That layer is the one that's responsible for making that decision, either classification or regression, giving you the final answer. That's the output layer. Whatever comes between, it's called hidden layers. It's hidden, it's just basically, they'll technically see this, you don't see those, so it's hidden to you. Like it's a hidden layer, basically. Now, we're going to start with first type of neural network, which is called fully connected neural network. Okay. The term is kind of trivial, so it's like a fully connected. That means all nodes are basically between every two layers are connected to each other. There's a connection between every pairs of node within two layers, two consecutive layers, basically. So we are going to start from here. So because it's fully connected, from input, there should be one arrow from each node to every node in the next layer. Then one arrow from here, here, and here. Then we are going to add a +1, which is the bias term. And that's also going to give one arrow here, one there, and one there. Okay. And this one, I'm going to make it shorter. And then here we also have a +1, a +1. I will leave the bias outside of the layer format because it's not, so when layer has a parameter called layer size, for example, we say size of this layer is 10. That's excluding the bias. So that means that layer has 10 neurons, not 10 neurons and a bias, right? So the bias, leave it outside, basically. And then here also, there's going to be a one-to-one connection, basically between every two layers. You're going to create a connection among all the neurons, basically. And then from here, you go to the last one. Also, there's a bias term. Then here you go to the last one and bias. and you make the prediction. Now, the prediction, which is the hypothesis that we are trying to learn, h of x, basically. One thing to remember is that when we are talking about this output layer, so we said about the input layer, the number of nodes are basically representing the number of dimensions that you have. When you go to the output layer, the number of nodes in the output layer representing on what you're trying to predict. If I'm trying to predict a regression problem, one number, I just need one node. If I'm trying to make a classification, like let's say I'm trying to predict 3 class, cat, dog, bird, then I need to have 3 nodes. One node representing a dog, 1 cat, 1 bird. If it's binary, now from the other end, you could represent binary either with 1 or with 2. Because if you just have this one, the other one is 1 minus, right? But you also could use 2, right? Now, depending on the task that you are doing, let's focus on output layer first. So every neuron has an activation function, right? It gets the Z and pass it to an activation function to make a final, basically, or to make some learning, right? Now, when you deal with the last layer, if I'm making a classification like a binary and this one, so all I need to have is sigmoid on my last node. Basically, the node of the last layer, the activation function is going to be sigmoid. Why? Because whatever I get, I convert it to a value between 0 and 1 as a probability. Now, if I go with this one, or I go with this one, multi-class, then I need a softmax. Right? Depending on what is the task that you are trying to solve, the activation function of the last layer is kind of straightforward. If it's classification, you're going to do sigmoid or softmax. If it's regression, you actually don't do any activation, you leave it linear. Because Z is just a linear value, right? So that's it, that's a linear regression. So if it's regression, the last node, the layer node, doesn't have any activation function, it's just a linear. But classification, basically, you do one of those scenarios. Okay.
Can we use tanh for the last one?
You can. Then you need to basically cut it on bit, find the threshold. It's giving you a larger range, right? It does the same thing as a tanh and value. Technically, they do the same thing. It's more common to use tanh and sigmoid. It's more common to use sigmoid than tanh, but yeah, that's also does because it's give you a binary value. So now, is this clear so far? All right. So now let's define a couple of things here. So we said we have input layer, or we call it here, for example, let's say L1. This is L2, L3, and L4 here. All right. And between every 2 nodes, there is a connection. And that connection has a weight value, right? So here I will write W, L, maybe rather than L equal to, let's make it consistent. I will say this is L, this is L plus 1, this is L plus 2, this is L plus 2. Okay. So this is WL, this is WL plus 1, so WL plus 2. Okay. Now, every arrow has one weight. Okay. So we're going to introduce the weight variable W. So WL I J. So W again stands for weight. It's going to be the weight between node J in layer L and node I in layer L plus 1. Yes, it's reverse. It's the indices I and J, we write it as reverse. So I stands for the node that we are connecting to. J stands for the node that we are departing from. Okay, so that means if I have this is node J, this is node I, and I plus one. Right? So there is a connection from here to here. This connection is called WL IJ. Weight belonging, this is layer L, this is layer L plus one. Weight that connects node J to node I in the next layer. And this one is WL I plus one J. Okay. Does that make sense? That's just a reverse instance. Now, okay, we are saying that. So this is for one between every basically pair. Now, if you want to write it as a matrix, because if you look between this layer and this layer, there is a connection between every pairs, correct? And every connection has a weight, correct? So if you want to look at the weight, how many weights in total do you have? No. Every connection has a weight. So you have 3 times 2. There are 3 connections, 1, 2, 3 nodes in the next layer, 2 here. There is a connection from every 2 other. So you have 6 connections, right? So let's actually
Include the bias.
no bias and weights are two. We're going to cover it later. So actually, let's write something here. N is going to be number of layers. So for example, if you say my neural network is size n, that means how many layers you have in it, okay? Including from input to the output layer, basically. Sn equal the number of nodes in layer n. Sn, we're going to size of that layer, okay? So now here, we want to show W as a matrix. If I look between, if I look at this WL means all the weights in this region, right? So I have one connection from this to every other nodes, right? And we write the indices reverse, IJ. That means this one comes first, right? Number of nodes in the next layer. So my matrix is going to be SL plus 1, number of nodes in the next layer, times SL, number of nodes in the previous layer. This is reverse just. And this is going to be basically WL, because it's always L, because this is for the layer L. Connecting to node in the next layer, node 1, from node 1, is going to be WL 1, 2, going to be WL 2, 1, WL 2, 2, WL 3, 1, WL 3, 2. Okay. And this is just for the example that we have here. Otherwise, this matrix is SL plus 1 times SL. Okay. So that's the weight matrix. Now, we have the same thing for bias, BLI. Okay, bias for layer L, connection I. This becomes the bias term from layer L to node I in layer L plus 1. So bias is just one line that connects. So here, if this is the bias, so this bias from here will connect to every node in the next layer, right? There's just a forward connection, right? And every one of those, so this is a plus 1, Similar to linear regression, remember we add the column of 1 and we learn the theta 0. Here also we add the basically a +1 and we are going to learn that theta 0. And with theta 0 we call it B. So BL, L, and I here stands for the next node. Here becomes I plus 1. So that's the bias term, connecting from layer L to the next layer node. Okay. So now, how many, if you want to write bias with respect to like as a matrix or vector, how many bias term you have?
SL plus 1 into 1.
SL plus 1 to 1, right? So one for every node in the next layer. So next layer has size SL plus 1. So it's going to be SL plus 1 times 1. BL 1 all the way to BL SL plus 1. One bias term for every node in the next layer. Okay. Is this clear so far? Okay. So we have the W's, we have the biases. Now let's break down the next one. Z. Okay. So if this is layer L plus 1, and this is node I, and this is layer L, and has basically 3 nodes and a bias. Okay. Call this, 1, 2, 3, just 3 nodes. We know every connection has a W, right? So we're going to write this W L I1, W L I2, W L I3. And then there is a bias term, become BLI, correct? This is, we have 3 nodes in the layer L, and we have a couple of nodes in the next layer, but we're just focusing on one of those, right? So when we write Z L plus 1 I, okay, that is the row input to the node I from previous layer, okay? And we always say that this is simply a weighted sum of all those arrows. Every arrow carries a data and has its own weight. You simply multiply weight by the data and sum those across those arrows plus the bias term. So it becomes a summation over J from 1 to SL, number of point nodes in the previous layer. In this example, SL is 3. Bias doesn't count again, okay? So weighted sum of WL IJ times, we're going to, here, I'm going to write it as AL, I'm going to tell you why, ALJ, plus a bias then, BLJ, BLI, sorry. Right? So now, just bear with me for this A, and I'm going to tell you why A. Now, so this is for one node, right? Now, if I want to write it as a matrix form or vector form for layer L plus 1, this is layer L plus 1. How many row inputs do you have? L plus 1, right? SL plus 1 basically. For every node you have 1. So this is going to become a vector of SL plus 1 by 1. So Z L plus 1, 1 all the way to ZL plus 1, SL plus 1. Okay. Now, let's focus on this A. Why I put A over there? Because every neuron has an output. An output of a neuron is that activated value, activation map, or activation value, right? So it's not X anymore. X only exists in the first entrance to the neuron, to the model, is where you have the raw data. But after the first layer, you don't have X anymore. Everyone has done some activation value on it, right? So this is going to be, we're going to define as AL, I'm going to write it as J, which is the activated, actually, let's write it with respect to this, AL plus 1I. That means the output of this neuron, it's simply a function over whatever is the rowing. But it's nothing besides just some function which gets a real number and produces basically another real number. And all of these arrows that you see from the previous nodes, they are also the activation from those nodes. That's why I use AJL rather than X. So similar to here, every layer has SL plus 1, or depending on the size of the layer, activation value as well. So if you want to write this as activation vector, basically it's going to be SL plus 1 times 1. All right, is this clear so far? Yeah. Okay, now, so this is the main idea of basically how this neural network works. So we have the building block, we have the definition of functions, we defined it how basically we're going to create a neural network. We're going to stack these neurons after each other and we create series of layers, right? And then these are the definition of parameters that we're going to use. Now, let's focus here on this N. So the size of a neural network comes basically defined by N, how many layers you have. Then, how many nodes in every layers you have. So you have N, number of layers, you have Sn, number of nodes in that layer, right? So now think about the problem. Like, for example, if we say a GPT model or a large language model has 30 billion parameters. What does that mean? So in this example, let's just say what are the parameters. So the parameters are whatever you are learning, W's and B's, any learnable basically parameter that you need to basically learn, right? So W and B, and let's see how many we have here. So we have 2 times 3, 6 plus 3, 9, right? Then here you have 3 times 3, right? And then you have plus 1. Then you have 3 times 1 and plus 1. So let's say, for example, we have, I don't know, like we have like 40 parameters here. Now think about when someone says we have 30 billion parameters. When we say large models, why they are large models? Because all those parameters, that means you have series of neurons, series of layers after each other, a stack of layers, basically. It's like layers and neurons, large models, right? That's why you have such a large amount of parameters to learn. And the idea behind neural network is that neural networks is capable of learning really complex pattern, right? The more complex your data and the more, basically the larger amount of training data that you have, okay, learnable data, not repetitive data, learnable data. You always end up, in order to, like when we create these larger models, we want to learn those, basically we need to create a larger model, right? Because what neural network technically does, you know, we learn, but it's kind of like a memorizing. We basically memorize the data. So when they create those large models and they become super heavy, super large, and like most of them, basically almost none of us can run it by ourselves. We need to have computational power, really large amount of GPUs that are running, you know. The reason is that because there was so much data and we wanted to learn it. So basically with neural network kind of memorize that data, right? So in order to do that, you need to have more parameters. Right? Those parameters are going to be responsible for mimicking or basically memorizing that data that you have, right? So your model, whenever you develop a neural network on some platform like, I don't know, Python or TensorFlow, whenever you develop it, at the end, when you develop the model, it tells you at the bottom of the page, it tells you how many learnable parameters you have. The number of learnable parameters decides that how complex is your model, basically. How heavy is your model? The more parameters you have, the heavier, the slower the model gets. So keep that in mind. So if you want to develop a model, if you have some problem like complexity issues, your model running slow, you can look at the number of learnable parameters that you have, and based on that, decide if maybe I need to drop a couple of layers, or maybe I make my layers smaller, right? Because again, there are two hyperparameters here. You have number of layers, and then how large is each layer, how many nodes you put in each layer, right? Now, so this is just a building block. Now we want to see, okay, how does neural network work actually? How we are going to learn this W's and B's? So we're going to start with something called feed forward, okay, or forward propagation. Forward propagation. So the building block of learning neural network is there are two main algorithms. For all neural networks, it's the same thing. There's a concept called feed forward or forward propagation, which the idea is that to propagate the data all the way to the end of from the beginning all the way to the end of the neural network, forward propagation. And then the second part is backward propagation. Or back propagation, or feedback. Well, there's so many names for it. And the idea is that in order to train a neural network, you need to have a data, pass this data, feed it forward all the way to the end. Okay. One thing to remember here is that learning in neural network happens backward, not forward. In the forward pass, you are not actually learning. You just have this data. Your weights and biases are there. You pass the data and you just propagate it forward. You multiply the data by the current weight and biases that you have, pass it to activation function, and keep passing it forward until you reach the end. So you're not learning it. You're just making prediction. You already have the weights and biases, right? Learning happens in the backward process. In backward process is where you get the prediction, you have a cost function, you have the actual value. You do a comparison, you find how much is the error. Based on the amount of error, you do a backward process. In the backward process, you start taking gradients and finding out that how much is the gradient for each W's and B. So you do the whole backward process from end to all the way to the beginning. When you reach to the beginning and you calculate all the gradients, then you update the gradients. You don't do midway. You need to do full forward, full backward, and then update the gradients. So basically, let's say we have just this input. We have this. I'm going to just write it as a hidden layers, and then we have output layers. So forward means this process, okay? Then you have a J, which is a cost function. So this goes here. Then backward means this process. When you reached here, then you update the W's. Now, let's make one example. Something that I know some of you have done neural network before, but let's see how does it backward work. Let's say we want to make a regression problem. We want to solve a regression problem, right? And this structure that we have in the class is a neural network. Every row is a layer. Every student is a neuron as a processing unit, right? So last layer, the last three students we have at the end, they are the original dimension of the data. We have 3 columns, and each student has a value about the house. Like we want to predict the price of the house. So we have 3 students at the end. Each student has, one student has the number of bedrooms, the other student has a square feet, the other student has, for example, I don't know, number of bathrooms. That's an unlucky one. So, and what we want to do is that we want to propagate that data all the way forward to reach to me. And I'm the regression, the last node, just call out, just do a linear regression. So look at the way that this learning is going to work. So if we say that there is a connection between every node, which is here, every student in the last layer, and every student or node in the next layer after, right? So it's going to be one-one connection. So the last three students, they will basically, each of them has one information. They don't have the same information, different information. But they are going to share whatever they have to every student in the next layer. But they also share a weight. So when, for example, one student that has the number of bedrooms tells to the exact student in front of him or her, that their house has 3 bedrooms multiplied by 0.5. My weight is 0.5 for that given student in front. But for other students, that person has a different weights. So we will share the same information that to the next student says that, hey, the house has 3 bedrooms, but my weight for you is 0.8. Because the idea is that we want to learn different. We don't want everyone to learn the same thing, right? So that information now has propagated to the second row. Second row of students, each student in the second row has received 3 information from the previous 3 students, plus a bias term, right? Now, first layer, which was the input, they don't have activation function. But the students in the second row, which is this row, starting from here, after they receive that input from the previous students, they also have let's call it a learning. Like they have their own call. Like they get the raw input, they sum all those information, then they mix, they think a little, okay, I think I'm going to call this. They have some activation function, their own learning basically, right? They apply their own activation function to that value and pass it to every student in front of them in the next layer, right? And now this propagates all the way forward. Every time, every one of you will receive information from every student in the previous row. You will sum those information and you make a judgment call on it yourself, depending on some activation function, for example. And you share that information plus some different weights to every student in front of you. Now we will reach to this last row, right? So we have 2 students. They received the information from the previous one, and they will apply their own learning and they pass it to me. Because it's a regression, I don't do anything. I just simply sum whatever the value they give me plus the bias term, and I output that as of the output function, output value. Or y hat, price of the house. Now imagine we have a cost function here, okay? And I also have the actual value. So I would go here and I say that, okay, we predict 400K dollar, and the price of the house was 500K. So based on the cost function, I would say that, okay, we are 100K short, right? Now, this 100K this error is not for these 2 students. It's a compounding error populated by every one information, because every one of you got some information. You did some learning based on your own basically activation function and adjust the value and share it forward. So you all are responsible to the portion of that error. But the goal here is that how to learn what is your portion of that error, right? So in the backward process, we want to calculate the gradient, basically. This because what we know what's a gradient. The gradient is that if I have a function, if I change this value by this amount, how much impact it has on the end, correct? So if I figure out the gradient of every student with respect to a cost function, I know basically how much I need to tweak the learning, the weight between that we have, in order to fix that 100K, right? So I start doing a gradient, basically backpropagation. I will backpropagate that 100K form of the gradient, taking a derivation of it, backward. And then these students, they get the amount that is their gradient, and then they look back and they look at every node connecting to them, every student from the previous day, and says that, hey, I got, for example, 40K gradient You told me this, you told me this, you told me this. This is your share. And now they get the gradient share and they propagate it backward. So this goes all the way to the last layer, which is the input node. They don't have gradient. They just, when we get to that point, we know we have calculated all the gradients. Then we have all the gradients, we apply those gradients using gradient descent to update all the W's along the way. And then we get a new example and continue the process. So you repeat this process backward, forward, until you get to a convergence condition. You know, you are not learning anymore. It doesn't matter how much back and forth you do. Right? Then you basically stop the learning. So that's the building block of neural networks, like the building algorithm behind it. It's like a forward, propagate the data forward, do a backward to learn, adjust the parameters, and continue. Do you think that's clear? Yeah. All right. So now let's convert that to some math. We need to use the same. Let's say in the last layer we have 2 nodes. So in the last layer we have 2 nodes. We're predicting 2 values here, right? And then we have the cost, and then we have so that's the general form of neural network. We're going to first define a cost, basically cost function, that J, right? So J for W's and B's, cost function with respect to W's and B's, is going to be basic cost function in general. We write it has 2 parts. One part is called goodness of fit, which is simply so this is called goodness of fit. Basically what it means is that how good is our model. This could be anything that you have seen so far for regression classification, goodness of fit. So that's one, and is average over all data points that we have. Average error, basically. Plus, we need to regularize the neural network because of this idea, because of they are so large, they easily overfit. So you need to always basically apply regularization to neural networks. Okay. So now there is a big difference here. So far, every time we did the regularization, our W weights that we are learning in regression, SVM, whatever, they were all 1 vector, size D. Right? In general, like any classical machine learning up to this point that we solved, our parameters, the W's, were always fixed length D, how many columns you have, right? So when you did a regularization, you apply a norm 2, for example, norm 1 on that vector. But when you go to neural network, we don't have 1 W anymore. You have 1 matrix of W between every 2 layers, right? So in regression, you only had this part. This is your regression, right? That's a regression. And in regression, W is just a vector of size D. Now, in this problem, you have, if this is the connection to 1 node, you have SL plus 1 of this, right? Every layer has, basically, every layer has this many nodes, and it's connected from every node in the previous layer, and there are W's among them, right? So between every two layers, you have a WL, which we define to, which is SL plus 1 by 1. So if you want to regularize W, you don't regularize it one, you need to regularize it at each layer, right? So it's going to be a regularization over summation. So this is summation because you have series of layers. J from 1 to n minus 1. N minus 1 is n is the number of layers you have. But why n minus 1? Because the output layer doesn't have W's, doesn't have weights, right? Output layers gets whatever from the previous layer, either applies some activation or no activation, and prints out the output. There is no W's outside, right? So that's why we only have W's here, here, here. So here you see we have 4 layers. We have 4 minus 1, 3 set of W's. So it's going to be always n minus 1. Now, so we need a norm here. We need to apply some sort of norm on W. What norm would you apply? Think about the definition of norms that we have seen so far.
P. On P.
P.
Yeah, so like a random norm. But we need a dynamic norm for each.
Okay, define what was a norm? Any function that gets a vector and produce a real number, right?
Yeah.
What we are dealing with here, WL, is a matrix. What norm you apply to matrices? Frobenius norm. Right, so you cannot apply norm 2, norm 1 because it's not a vector, it's a matrix, right? So we are applying Frobenius norm. And Frobenius norm, we also know it has a square root. So you put it power 2, so the square root cancels, and it's 2, and there's 2 basic derivation that cancel each other. Okay, so this is the regularization term. Or weight decay. Weight. Right. So, and so far, this goodness of it could be anything, depending on the problem that you are solving. Any cost function that is basically suitable. Now, if we want to calculate, basically, if you want to calculate the gradient of J with respect to one of the W's, right? So basically, you need to take a derivation of this one. I'm just writing it like that because we don't know what's J. Plus, you need to take a derivation of this with respect to WL. What's the derivation of this with respect to WL? Frobenius norm is simply a square root, right? Values to the power of 2 plus plus, right? So this derivation becomes 2 times lambda, 2 and 2 cancel each other, becomes lambda WL, right? Derivation of that with respect to WL. So the summation goes because you do with respect to one of the L, not all of them. And the derivation of Frobenius norm to the power of 2 is basically 2 times the value. And 2 and 1 over 2, they cancel each other. Then you have derivation of this with respect to BL, which is simply and whatever the cost function that we use. That's going to be the general form. All right, so this, what's the dimension of this gradient? In regression, when you take a gradient, what's the dimension of gradients? What's that?
D by 1.
D by 1. Why D?
Because D are the column.
You have D W's.
Parameters, yeah.
Here, when you did with respect to WL, what's the dimension of gradient?
SL plus 1.
Times
1.
times SL.
Yeah.
Whatever the gradient of a function with respect to a matrix becomes a matrix size. With respect to a vector, it becomes a vector size. So in regression, it was a vector, so the gradient is also vector because you need to find one gradient per W to update it. So if I take a derivation with respect to WL, I have SL plus 1 times SL in that matrix. So if I want to update every one of them, I need one gradient per. So same dimension, basically. Okay, say you will get same dimension. With respect to BL, BL is a vector, so you get a vector gradient. Okay, let's just keep that in mind. Now, let's look at this problem. Do you think if this is convex or not convex with respect to W's? So it's non-convex. Why? Because let's try to mimic the output of a network. So the output of the last output of the network is an activation function over the Z of that node, right? So the output of the network is f of Zn. N is the last layer. Right? The function over the last node is Zn. So if this is the last node, let's say. This is layer N, and this is the Z, and this is the A. Correct? Now, what is Zn? Is that summation term, correct? So this is technically, this is equal F over summation J from 1 to Sn minus 1 W n minus 1 1 J A J plus V n minus 1. Correct? Now, what is A? A is a function over Z to that layer, right? So this is the F of summation W, F of summation W, F of summation W, F of, you see that all of that process? So because of all this because of this relationship is non-linear with respect to, non-convex with respect to W's. So it's not a convex problem. That means the only solution that we have is iterative solution, something like gradient descent or different techniques. But at least you need to basically solve it iteratively. You cannot basically solve it in one go. Now, it doesn't have a closed room solution. So if it doesn't have a closed room solution, that means it has a local solution. If it has local solution, that means that every time you solve it, you're going to get different answers. That means if you solve neural network, you need to solve it multiple times and pick the one that gives you the best answer. Okay. Now let's assume one cost function. So let's say the goodness of a fit for this example here, for this one, that cost function, I'm going to assume it to be, because we have two outputs, 1 over 2 summation I from 1 to 2 yi at minus 1i to the power of 2. Okay, I'm going to assume that cost function J over there, the goodness of a fit part, okay, is this simply error, square error, and average for 2 because there are 2 nodes. Okay. So yi we know is a so n stands for the last layer, a n I stands for how many nodes in that last layer, right? Minus yi to the power of 2. Okay. So now we want to talk about that how we are going to learn this backward process, this concept of the gradients. So to throw another network, unfortunately. It's going to make it simple network, okay? Imagine you have something like this, and this is the J that we have, okay? When you calculate the cost, the idea is that we want to propagate, backward. This is and update the problem. So in order to do that, we're basically starting taking derivation, find the gradients, right? So your goal is to find the gradient of this cost function, or gradient of basically that the error function that you have with respect to everything here. For example, with respect to W's, B's, right? And these are different, they are different W's, right? So I just don't put this. Your goal is to take a derivation of J with respect to all of those and find the gradient of each and update those, right? But one problem is that, so one of the problems that we had previously in neural network was, it was inefficient, this is just some years back. And so if you try to calculate this gradient with respect to here, no, it's fine. If you try to calculate this gradient with respect to here, okay, you might be able to do this fine. Try to calculate the gradient with respect to here, then you're going to have some problems. Why? Because think about this. Function, right? To take a derivation. These are not easy derivations. They're going to be really complex derivations, right? So going from here to here is not efficient, and sometimes it's not possible. We couldn't solve this neural network, right? So the idea that this breakthrough that we could all of a sudden, the neural network become more efficient was, rather than trying to solve this gradient in one shot, try to break them into smaller gradients using a chain rule and propagate slowly backward. What does that mean? That means rather than going from here to here, I go from here to here, then I go from here to here. Now, if I want to go to here, for example, I already have calculated up to this point. I don't need to redo it. I just need to go from here to here, then from here, for example, to here. And then from here to any weight, basically. And then here to here. So that's propagating the gradients backward, but using a chain rule. So we break it down rather than having one shot problem into smaller problems, which are much more efficient and much easier. We will see that much easier to solve, because you couldn't solve it in one go. Okay, but something to notice is I focused on every main step to be toward the node, right? When I back propagate, all the arrows that I created, I say I go from here to here, then from here to weight, then again from here to here, not from here to here. So when you go backward in the gradient, your goal is to calculate the gradients of the error with respect to the input of every neuron. That's your first step. find the gradient with respect to the input to the neuron. From there, you can calculate the gradient with respect to W and B. You first need to go to that input part. Same thing when you do forward pass, you calculate the Z and then activation and then pass it forward. Backward, you also need to go to Z first, and then from Z go to W and then Z go to B. Right? So now, here, this is our cost function, and this is the layer, right? I want to calculate the gradient of this. So there are two parts, depending on how we want to solve it. This one has an Z and has an A, correct? So you can actually first calculate with respect to A, and then from A go to Z, right? Or you can combine them if it's that one operation. You can, rather than doing both, you can just do it one. Okay. So because we know A is always function of Z, so it's much easier to just go in one go, right? So here, I want to take a derivation of this with respect to Zi. Okay, Zi here, this is Z1, this is D2. I want to calculate the derivation with respect to any of those two, right? So this is the cost. Okay, this is the formula. What I'm going to do, let me say, so if I wanted to calculate the derivation with respect to A, I would just take a derivation of this with respect to A and it comes out, AI basically, right? So but I don't want to do that. So I would just take a derivation with respect to Z, because I know I can write this as F Zi minus yi, correct? So I would just directly calculate the derivation with respect to Z. Now, so let's take a derivation of this one with respect to Z. This is a function which we don't know what this function could be, sigma, it could be softmax or whatever, right? So I would just write as F prime Zin, the derivation of that, times 2 and 1 over 2, they cancel each other, and then because this is with respect to same index, so this comes out, so it becomes F Zin minus yi. Correct? So that's the derivation of this with respect to that, which basically is F prime Zin times Ani minus yi. Correct? So that's the derivation with respect to Zi. Now let's see. What if I first actually took a derivation with respect to A? So let's say, okay, I will first take a derivation with respect to AI. So what do I get? So 2 and 2, they cancel each other, basically comes out, if I take a derivation of this with respect to AI, comes out AIN minus YI, correct? So we say that we're going to solve it in two parts. So first, if this was J, I go to beginning, which is A, then from here I go to here, Z, right? So that means now I need to take a derivation of A with respect to Zi. What was A? A is a function over Zi. So I don't know the Z, so I will write it as F prime of Zi, correct? Correct? Now, look at this idea. So from here to here is exactly the same as if you multiply times which is this times that is exactly equal to correct? So that's why rather than solving this in one go, we break it down in a smaller piece and you just multiply them by each other. That gives you exact same answer. But now you don't need to deal with such a complex gradient anymore. They're much easier, much faster, and you can even distribute this among in your basically code, but to make it much faster. So is this clear for everyone? Right? Okay. Actually, so we are going to introduce this, the gradient of cost function with respect to the input to a neuron. We're going to write that, just introduce a variable for it, sigma in. So this stands for the gradient of cost with respect to z. Okay, so this sigma in. I stands for the node, n stands for the layer that we are referring to. Okay. So now we have the gradients from here to here and from here to here for both of this. This is the same formula, right? So we have reached up to that point. Now, we want to go from here. I'm not going to focus on W's yet. I want to see that how I can go to the next Z. So I want to go from here to the next Z. Either I could go to A and then do the same thing to Z, or I can just directly go to Z. Because it's again that those two are always really close to each other. A is a function of Z. So I can basically directly go from here to here, always to the beginning, to the input node, input part of the node. So we are going to define, let me draw this. So let's say this is layer N. I'm going to just make it more, I'm going to write just L plus one, some layer, doesn't matter, right? Some layer. And this layer has, let's call this node 1 to all the way to node 1. This is node I, and to SL plus 1. Okay, that's a layer which has SL plus 1 nodes in it. And then this is a layer L. Okay, and this is node J. This is node J. Okay. So let's assume we have this sigma L plus 1 I. Okay. Let's assume I have the gradient up to all of these regions. And that means I already have reached to here. Okay. In the example, if the imagination is difficult, this is the same rather than L plus 1, assume N. We already solved it, right? So let's assume you have that. We want to see that how could we go from there to one layer before that? Okay. Again, if to make it, let's just make it easy because I feel like some students. N and N minus 1. N is the last one and N minus 1. Now, rather than 2, I have 3 nodes in it. Okay. So that means let's assume, or we already proved it actually. Let's not assume. Let's say we have this. We have that. Now, my goal is that, okay, I have reached all the way here. Now I'm interested to calculate the gradient with respect to this. Okay. So to calculate the gradient of cost with respect to Z layer N minus 1, one layer before node J. Okay. So in order to calculate that, think about the example that we just talked about. When you traverse the information forward, you just didn't share it with one student in front of you, you share it with every student in front of you. And to every student, you say to multiply it by some number. So if you want to get penalized or gradient, you're not going to get one. You're going to get one from every student who you share the information to, correct? because your input caused some error. So here, this node doesn't just give the data to this, it gives the data to every node in the next layer. So there is a one connection to every node in the next layer. So when you go gradient, your backward is from here to here, is from here to here, and from here to here. You get 3 gradients. You're going to accumulate those gradients together. Right? Because you basically share the information forward to all 3, so you get the gradients from each. So this cost function, if I want to write it as a chain rule, because I already have this part, so I will write it as a summation over I from 1 to Sn, number of nodes in the last layer. Gradient of cost with respect to raw input to the nodes in the last layer, and then take a gradient of Z and I with respect to Zn minus 1 J. And I'm going to sum all these gradients, these are these 3 arrows. So this times that, plus this times that, plus this times that. That is the gradient to every node in layer n minus 1. So we already defined this. So we say this is Ni, right? We already defined it. Now let's look at this part. So, we already said that Z equals, so Z, Zni, which is a node in the last layer, gets information from every node in the previous layer plus a bias term, right? Which is summation over J from 1 to Sn minus 1, W n minus 1, I, J, A, n minus 1, J, plus B, n minus 1, I. Correct? That's a definition of input to any of these, right? So, I'm trying to take a derivation of this for every, so this arrows. I'm talking about right now this arrow, and this arrow. Doesn't matter which node we are talking about. But I'm trying to calculate this gradient. So in order to take a derivation of this with respect to Zn minus 1 I or J, first I'm going to write this as of J. So it's going to be Sn minus 1 J from 1 Wn minus 1 Ij f of Zn minus 1 J plus Bn minus 1 I, right? Because A is always a function over J. So you want to take a derivation of this with respect to Zn minus 1 J, which becomes Wn minus 1 Ij f prime Zn minus 1 J. Correct? Derivation of that term with respect to one of the J's. So now you bring that and you replace it here, so we get Wn minus 1 Ij times f prime. And what we can see here is that this is a summation over I. J doesn't have I, so I can basically bring it outside. So this could be summation Sn I from 1 to Sn sigma n I times Wn minus 1 Ij times f prime Zn J. And this is sigma, basically L All right, let's write it n minus 1 j. That was sigma in. This is sigma n minus 1 j. You basically calculate this chain rule, you broke it down, and this is what you have. And what basically it tells you that the gradient of cost with respect to raw input to this node, or the input to this node, right, is a multiplication of this times the weight that was on the arrow times the gradient of the activation function of that node. And you sum basically those together. Okay.
So can you explain this part again, how this equation came in the rectangle? Like we substituted this, yeah, that.
So you have this part, right?
Yeah.
So this one, this is summation over I, correct?
Yes.
So J doesn't have I indices. It's a fixed number. This is a fixed value, right? That I'm multiplying by this by this equation. So I brought it outside. Y is a fixed number because this is a derivation of activation function. So a node has Z and has A. Same A will be shared to every node in the next layer. Same value. So this derivation is constant for all nodes in the next value. The only difference is they have a different W's. So that's why you multiply this W by this and time at the end, you sum all of those and time it multiplied by that. Let's do the same thing. You can do it just in this way or that.
Okay, so like Z over J over there, it has to be n minus 1, right? At the end. Or should it just be n?
N minus 1, you right. Thank you. Yeah, this one is n minus 1. Yeah. Thanks. Okay. So is this process clear so far? The way that we are propagating this basically gradients backward. All right. Okay, so now this definition of gradient is only for last layer. Remember, this specific one is only for last layer. Why? Because last layer is the only one who's directly connected to the cost function. So you take a direct derivation of cost function. This one is for every layer L from 1 to n minus 1. So the same formula you use for every layers except for the last. For last one, you use directly that. Okay. So now we have that. So the next thing is that we just calculate Z because from Z we want to reach to W and B. So now we want to calculate the deviation. Another one. This time I will write that layer L plus 1. This is node I. Okay. And node I receives all these arrows. Okay. And here we have and this is layer L. And here we have WL I1 and J, WL IJ and WL ISL. And this is BLI. So we want to calculate the gradient with respect to W's and B's. So we already have this shaded region, gradient to up to that point. Now, all I need to do is to go from here to here, here to here, here to here, and here to here. And that's going to be the gradient with respect to W, each W's and each B. So in order to do so, this is the definition of Z, right? So we want to write the gradient of J cost function with respect to WL ij. Like let's say this one. Okay, we want to calculate this gradient. And by chain rule, we already know that it's going to be this times that. Okay. So in order to go to this one, remember one thing, when you work with W's, each W is only connected to one node, not multiple nodes. W's are unique. Each arrow carries its own W. So if I want to go update this W, I just need to go directly from here to here. There's no any other node. It's just one direction, right? So this becomes the gradient of cost with respect to that ZL plus 1 I times the gradient of that ZL plus 1 I with respect to that WL IJ. So this is that's that. And any of these arrows is the second part. Okay. Now we already have this, so we say this is equal sigma L plus 1 I. This is this part, right? Which we already proved. It's one of this form, basically this form. Then we want to calculate this part. We want to take a derivation of Z with respect to WIG. What is Z? This Z, right? You want to take a derivation with respect to WIG. What do you get? AIJ. AJ, correct? So this basically becomes times A from the previous layer, which is LJ. So in order to calculate the gradient of the weight, that's why we always go to this node, right? Because if you reach to the beginning of every node, all you need to do is multiply that already have gradient by the exact output that you received from the previous node, and that's the gradient for the weight, the connection. The gradient of what you had times, because remember, every arrow, I said, assume it as a tube, right? It's like a pipe. Data goes through it, AJ, and then the size of this pipe, imagine, is the WJ, right? So in order to update this W, you multiply whatever you have all up to this point times the data. That becomes the gradient for the weight, right? So it's like it doesn't have much computation. It's just simply what you have times the whatever output you already have. So that's why also you need to remember, not if you use TensorFlow or something, but if you use Python, like you write your own neural network, you need to keep track of everything when you do forward pass. You don't do a forward pass and get rid of them. No, you keep them in the memory, because when you go backward, you don't want to recalculate values. You can just simply say, okay, what was the AJ? I already have it, right? So you can use that. Now, if we want to take a derivation of this with respect to B, the bias term, that's also going to be the same thing, this one with respect to times this one with respect to B. So which is this times, what's the derivation with respect to B1? So that's the same thing then. So that is the gradient with respect to W, and that's the gradient with respect to B. And these two formula are for every node layered from node, basically go 1 all the way to n-1, because last layer again doesn't have W's, right? It's just from the first layer forward, you basically have the W's. Last layer doesn't have any W. Is this clear? All right. Any questions? So that's good. There's no question. I take it as a good sign. So you should be able to get a neural network and do these small derivations and multiplications, right? So just keep that in mind. Okay, now we can write this as a actually let's discuss something here. Let's look at this bias term. When we take a derivation of bias term, the derivation of bias term is exactly the derivation of the node, right? But let's see why is that? So this is a node, and these are the arrows to that node, and then this is the bias. There's a +1, whatever +1 times bias, basically that's it, right? Let's see, what does bias do here? Basically, you do weighted sum of all these arrows plus the bias, correct? Look at the impact of bias. So you already received the data from every node behind you, right? Because every other neurons. They give you data that you have learned. You basically weighted sum all those basically learning. And then all of a sudden you say, okay, it's short by 2. I'm going to add a 2 to it. Imagine bias is 2. That's all the bias does, right? You just add some number to whatever you have received, correct? And the idea is that because we are learning that bias, the idea is that we have some idea of that the previous nodes are always short by this much, and this bias value is going to fix that problem. That's what the bias does, right? So we always up, basically, or could be down, whatever the values that we are getting, right? But when we going a backward process, when we are getting to this point, so I have the gradient up to here, right? Which gradient basically says that how much you need to adjust the weight. For this one and this one, you directly go from here to here, and you say that, okay, you give me this information, this times that's your gradient. But when we go to the bias, when we look at the bias, we exactly going to give it same gradient as what we had. Same gradient will be applied to bias. Why? Because bias was responsible for adjusting correct values. So if this node was short, for example, by some number in the data processing, bias was responsible to fixing that. So you adjust the bias with exact same gradient because, hey, you were there responsible for fixing whatever data that I get to, if we know there is short by this much, you were there to bring it up. But you didn't bring it up, I got this much penalty, so you need to fix that this much exactly. So that's why you see for bias, we get exact same value because bias is just there for us to shift the line. Think about it in a regression. If this is the bias, intercept basically bias that we are learning, and then it was supposed to be that, right? So we exactly update the bias by the amount that is shorts, right? Hey, no, you need to be here. So here is also the same thing. We exactly increment the bias by exact amount that is basically short. Okay. So that's why the bias gradient, it doesn't have its own gradient. It's just gradient from the next layer. Okay, now let's write this in matrix vector form because, especially neural network, if we can write that in a matrix vector form, it becomes much more computationally efficient for us to calculate that. So we can write the sigma n, which is gradient for the last layer as of an minus y element-wise multiplication of prime zn. See the dimensions swap because this is like a matrix vector form. Sigma L T stands for transpose. Okay, so it's a matrix vector form. So that's basically, rather than having it here, we wrote it with respect to each individual as like indices. So that becomes basically the matrix form. Okay, now. Now let's write down the pseudocode for backpropagation algorithm, forward backward in neural network. So if you want to write your own neural network, basically, these are the steps that you need to follow. First, just let's define n. That means how many layers I want to have. Okay. Then you will define SL, L from 1 to n. For every layer, you define what is the size of that layer, how many nodes I will put in that layer. Then we define AL, L from 1 to n. An activation function that you want to use for every layer, you define what activation function you want to use. Okay, now this is important here to remember. Activation functions are constant among neurons within a same layer. So within a layer, all neurons going to have same activation function. But different neurons are independent of each other. Different layers are independent of each other. So layer 1 and layer 2 totally could have different form, different functions, different types. No, it's totally different. But within the same neurons, same layer, all neurons are identical. They're like just copy paste, basically. You put these neurons after each other. So you just stack the same neuron on top of each other. The only difference is that the arrows that goes out of them, they has a different weight. Otherwise, the function that they have is the same. They process the data exactly the same. They just have a different weight value. But again, in different layers, they're all independent. So that's why you come up with, okay, I have 5 layers. Layer 1, I'm going to use ReLU, layer 2, ReLU, layer 3rd and 4th, TANH, and layer 5th, I'm going to do, for example, signal. It's like your call, whatever you do. And how you pick which one is the best is kind of like, try and error. It just optimize for which one gives you the best answer. So that's one thing. Now, step 1. So we want to start a neural network. So we already have the definition of neural network. We need to define the W's and weights and biases randomly. So you do a random initialization for every layer has a W, right? So you're going to do a random initialization, randomly initialize WL, L from 1 to n minus 1. Remember, for weights is n minus 1 because last layer doesn't have W. And then B L from 1 to n minus 1. You're randomly going to initialize this. Now, keep this in mind. The neural network, it has a local convergence, right? So that means that random initialization could have a huge impact of how fast you converge or where you converge, right? So it's probably as a rule of thumb is try to do random initialization from a distribution, like a Gaussian or something, right? Don't put them all zeros or all ones, just it easily can go stuck in some local problem, right? So just random initialization maybe from a Gaussian distribution with mu and variance. That would probably be better. Okay, now we define the neural network, all the layers, nodes, and W's randomly initialized. Now what we want to do is that we want basically to do a forward loop and just basically update, right? So we're going to write a for loop, like a time dependence. So basically we'll see that for epoch in max iteration. Epoch means the every basically iteration is called epoch. For epoch in max iteration, what we want to do is that every iteration, we want to do a forward pass, backward pass, calculate all the gradients, and then update the W's in every iteration. But not only on one data point. You either do it over all your data points, like a full gradient descent. That means in every iteration, I will go over every data point that I have, do a full for every training data, doing a forward pass, backward pass, calculate the gradients, accumulate the gradients, and then average the gradients, because you have so many gradients accumulated, it's going to be something large, right? Or you do something like a stochastic gradient descent and you do sample from your data. Like if you have too much data, so I don't want to go through all of it in every epoch, so it's slow. So I do a stochastic gradient descent. So either way, in every iteration, before doing a forward backward, I need a placeholder to keep track of the gradients, right? So I will basically, this is step 2.1. I will create delta WL, which is just simply a placeholder, and this is going to be for L from 1 to n minus 1. I will create one placeholder for every layers to keep track of the gradients. I do the same thing for B. B is a vector. Now I will do a forward pass. So let's say I'm doing again, doesn't matter, full gradients and batch gradients, but I will write for I in range M. Okay, and here M is number of data points in batch or full data, depending on what you are solving. So I will start a second loop, loop 3.1. Now, when you start the second loop, you do one data point at a time, forward, backward. So basically, you're doing a forward pass, and calculate ZL from 1, L from basically 2, because that first layer doesn't have a Z, like it's just a row input, to N, and A same, L from 1 to 2. So I calculate, when I do a forward pass, you remember I told you keep track of all the Z's and all A's because you want to do a gradient backward. So (2.32). Now you do a backward. Probably that's right. Calculate cost 2.3.3 backward pass. So when you do a backward pass, you're going to calculate the gradient with respect to all W's and all B's, basically. Okay, and from 1 to n minus 1. So you calculate all those gradients. Now, because we calculate one gradient per data point, forward, backward, right? So what we're going to do is that we're going to add this to that placeholder that we have. Every one of these are a matrix by its own, right? So we basically, we would say that this plus equals that. And So now 2.35 is 10 for loop 2.4 basically 2.4. So 2.4 we finished the for loop. The second for loop basically 2.4. Then 2.5. Now we accumulated all these gradients. We're going to average this because it's so many gradients you put on top of each other. Otherwise, if you don't average, it's really large, right? Each data point found out that every nodes need to be adjusted by some amount. Okay. If you listen to all of them separately, then you're going to have a really diverge from everything. So what you do, you collect all those learnings, average those into one, and you basically think about it. The idea is, imagine this is one gradient, right? Maybe we can just do it here. So let's say this is the cost function, right? And let's say one of them says go this direction, one data point tells you, hey, the gradient should go that direction. The other one tells you goes this direction. The other one tells you go this direction, this direction, this direction, this direction, so on, right? So you cannot listen to all of this because you will diverge actually from the path that you want to go. So what you do, you average all of those, and assuming that the average, for example, is somewhere in between. It's a better path, basically. So in general, you average these gradients to move toward the goal that you have. Okay. So here we basically calculate this WL basically is equal 1 over M because we use M data point gradients. And also here it's going to be so that becomes the average gradient for W's average gradients for B. And we are going to finish the second loop also, sorry, not finish the second loop. So we did it forward and backward. Now we need to update the W's and B. So we have the average gradients. So in 2.6, you're going to do WL. It's like a basic gradient descent, right? There's WL equal previous W minus a learning rate times the gradient. What is the gradient? So gradient is that value, which is that. However, remember we have that regularization terms also, which the gradient was it was lambda WL. That's constant, it remains the same. Then you do the same for B. There's no regularization. So you update the W's and B, and then, for example, in 2.7, you check for convergence. And you, again, your choice of convergence, you can basically check. And step 2.3 basically is 3, yeah. And for loop. You finish the for loop basically. So this process is basically backward propagation, forward backward propagation. Right, can take 5 minutes. I can see everyone is looking, staring at me. Okay, just let's continue. All right, so this was a feed-forward neural network, and this is the backward-forward propagation. And any types of the neural network that you will solve out there, image classification, natural language processing type of deep learning models, they all work on the same algorithm, forward, back. Okay, so this is the same for all of this. The main difference among these different neural architects is the architect of the network, not how they basically forward algorithm work. It's basically how we stack them on top of each other and how are these connections among them. Okay, so this one, the first one that we saw was fully connected because there was a fully connection between every two pairs. The next one that we want to talk about is called autoencoder. Okay, so autoencoder is basically architects of neural network or types of neural network that generally has the following form. So there is an input to the neural network, autoencoder, and there's an output, and then there is two parts, an encoder, a decoder. Okay. And this one in between we call latent layer. Latent because it's hidden, right? So it's a hidden layer, basically. So or latent layer, or also latent representation, also we call it. Now, autoencoder is a types of neural network that consists of two separate neural networks. An encoder neural networks, a decoder neural network. These are two different neural networks. Okay, but these two different neural networks are going to work together in the same pipeline, basically. Okay, so when do we use this autoencoder, or what's the goal of this autoencoder? Its first thing is that basically is an unsupervised technique. That means it's not for classification or regression. It's unsupervised technique. Okay. There are a couple of things that we can do with main reason we use autoencoders is dimensionality reduction. Okay. So it's really similar to PCA with the caveat. The main assumption on PCA was data exists in linear domain. If you don't have that assumption, if you don't know about the data, if the data is not in linear and you want to do dimensional reduction, one good approach is autoencoder. How is a dimensionality reduction? We will talk about that later, but this is one of the usage that we have. It's really common. Two is clustering. Okay, we use this a lot for clustering the database. We're going to talk about it also. Three, let's say a novelty detection or some sort of anomaly detection. Could be for denoising also. That's a couple of things we can do here, but let's just stick with these three for now. So dimensionality reduction. Let's see how does this help with dimensional reduction. So first thing about autoencoder, which is different with other neural network types, is that input and output should be the same thing. It's unsupervised, so you don't have class label. It's not classification or regression. It's types of neural network that you feed a data to it, and you expect to give you back the data, the same data that you pass. Okay, but why? Because this model encoder, its job is to get the data, like it's like a funnel, right? It's get the data, compress the data into this vector latent representation. So this latent representation is kind of basically is like a it's the dense format of the actual data, really small. So imagine your original data is like 1 million columns, and you compress it to a vector of size 128. This basically float number from 1 million to 120. It's just an example. So that's basically what the encoder does. It encodes the data, compress it. On the other end, decoder, as the name comes, its job is to get that 128 length vector and reproduce the actual data. Okay, so encoder will compress the data, decoder will try to basically convert it or reverse it. Now, the way that these are two different networks, but how this process happens is that this whole training happens together. The forward and back, they work together. The encoder, in order for this to work together, okay, that means that, what is the goal? That means the goal is going to be to minimize the error, right? What is the error? Error is simply going to be, like, let's define a cost function. So the cost for this autoencoder is going to be average over cost of basically cost of xi input and what were we predicting? And this could be any cost function, for example. You simply, you're going to compare your input to the output directly, and you see how much this costs. For example, if it's a vector of number, that means it's a distribution, I will do probably a Keil divergence. A Keil divergence between this distribution and this distribution, right? Or some other cost function, you just simply say this one minus the other one, like whatever, right? You come up with those later. But this you will find out how much is the error of reconstruction error, basically. Okay. Now, because the error is when you do a forward, you calculate the error, you backward, you propagate backward. Same thing that we did before, right? In order for this to work together fine, that means to have the low error, encoder and decoder need to learn how to communicate properly, how to basically work together. What does that mean? That means encoder job is to learn how to precisely or really good compress the data into a representation where decoder, if it receives that representation, has enough data to reconstruct the input file. So again, encoder gets the data, compress it down, but not just to compress it down. It compresses it down to a really prime version, which if you pick that prime version and pass it to this decoder, decoder need to be able to reconstruct. So these two are going to learn together. Encoder will focus on how to improve the decompression, how to improve this compression act, and decoder will focus on how to improve the inversion act. They both have their own weights, right? So this one will focus to update its own weights so it can compress the data really good. This one will update its weight so it can inverse whatever it received back to the original data. So these two will work together to reduce the error. By doing that process, you will get to the point that this can precisely convert, basically encode this data to a really good representation, where this only needs this one to work with. Let's think about one example. This is not an actual example, but let's think about a scenario of YouTube. So when you go on YouTube and you want to upload a video, so there are two, let's assume there are two engines. One engine is for uploading. So you upload video. So YouTube basically again, this is just example, but let's say YouTube gets that data that we say it compress it, right? Because if in order for YouTube to store that data, it's not going to store gigabytes of video that you are uploading for everyone. It requires lots of storage. So it will compress it and store that compressed version of that into storage. Now, next person goes to a website and now they want to play your video. That activates the second part, the decoder. Now, decoder will get that compressed data and decode it, reconstruct the actual data. That's why when you upload the data, you see that even if the highest quality, you still have some loss of data quality in YouTube. That comes from its compression, decompression, right? So this is what we want, right? We do all this learning. After we reach to the point that we converge, we have the perfect model, learned everything. Depending on the task that we are solving, our need is different. So let's start with dimensional reduction. I have finished that training. After my training is done, I only need this part. I don't need this anymore. That decoder goal was to work with this so this won't become perfect, right? So if I'm doing a dimensional reduction, that means I want always to, whatever is my data, to compress it and use it for regression, use it for classification, whatever. So that means rather than using this in my original task, I'm going to use that vector. It's a vector, right? Even if you have an image here, you could convert that image to a vector and use the vector in whatever task that you have. Because the idea is that that vector has enough information that is representation of the data. So in dimensional reduction, you basically need to only keep the encoder. And every time you get the data, you pick that and you use for classification, for example, or regression or whatever. That's the task of dimensional reduction. And it's really similar to principal component analysis. In principal component, imagine this is acting like the U, principal components. You get the data multiplied by U, you get the X prime, lower dimension. And if you want to reconstruct it, for PCA, remember for your exam to know how to reconstruct, was to multiply it back again by U. So if you multiply this back by U transpose, now you reconstruct back the original data. So this is acting exactly like PCA, right? But it doesn't have the PCA assumptions, basically. Okay, so that's for the dimensionality reduction part of the task. Now, what about for clustering? So for clustering, one idea is that if you just look at this example, you'll pick this, again, the same thing, you pick that, and you do k-means on that. Right, so you compress your data into a lower dimension, so it's cheaper, and you do k-means. One other type of autoencoder is called a variational autoencoder, or VAE. Autoencoder, variational autoencoder. Variational autoencoder, basically it does something like this. So when it compresses the data, that latent representation of the data is going to be a bit different. We are going to learn two things here. This is a fixed length vector. These are going to be the same lengths, okay? This is going to be a vector of mean values. It's going to be a vector of standard deviation or variances, for example. What is the goal here? So in the variational autoencoder, rather than presenting the data into a vector and reconstruct from, you actually try to learn the distribution over that latent layer. In order to learn the distribution, I need to learn what are the means and what are the standard deviations. Because imagine here also, this is a vector, right? Has D dimension, like a P dimension P, okay? So if a vector has a P dimension, that means there are P values. Those P values, they're generated from some distribution, right? And we know here, for example, something like Gaussian, right? Because it's just a central limit. So we are going to learn for every dimension of that vector, which is P, we are going to learn the mean and the standard deviation for every dimension of that. And when we want to reconstruct, what we are going to do here, we are going to randomly sample from this mean and the standard deviation, generate a random sample and reconstruct a random sample. So this one compresses the data and learns the distribution. This one sample from that distribution, and it should be able from that sample to reconstruct the original data. If you learn that, you have learned the latent distribution over the data. If you have the latent distribution, it's a perfect approach for doing a clustering technique. You use those basically distribution and you apply some clustering. So that's called variational autoencoder. This is autoencoder. Okay, the cost function remains the same thing. It's just up in the center, basically. In one of them, you actually have a vector, you redo it. In the other one, you have a distribution you sample from. There's a sampling step, and then you create from that sampling, basically. Now, in the other one, which is novelty detection or anomaly detection, is imagine you want to you have a task. You want to create a model that is able to do anomaly detection for a really rare case, rare scenario, something that's really rare. For example, there was this we have this NASA challenge. This idea was that they released this satellites data sets, that these satellites that they're going through the orbit, and then they were, I don't know, 2 or 3, 1 or 2 data points where the satellite basically I think it's like deviated from its path by a small degree, which is not visible, right? But you know, those type of movements could have compounding effects, right? So the idea was that how could you come up with an algorithm that is able to detect that? The problem was that the data set only has, let's say, 2 examples of deviation. Every other example is not deviating. So if you want to learn it, you cannot use those 2 as part of your training, because how do you want to test it again? And they don't have any other data to give you. So you need to come up with a technique that does not see the deviation data, but is able to predict the deviation. So autoencoder could be something interesting there. Why? Let's say you develop which is, this is actually as a part of the, you know every project, every challenge that has these boards of like the top scorers. So one of them is, I think, is variational autoencoder. Someone solved it. So the idea is that, or something, or autoencoder, not variation. I'm not sure exactly. But the idea here will be that rather than trying to focus on the bad data, focus on the good data. And this could be any project that you solve. So you bring all the data that you're sure they're clean. Like in my example, if the domain that I work, which is cybersecurity, if we want to do basically threat detection, rather than trying to find, because if you always try to find what is a threat always changes every day. You need to constantly search online what's a new threat and try to come up with something new. So rather than me focusing on what is threat, we focus on what is a normal behavior, what is a good behavior. For satellite, you focus on what's a correct approach. Correct? So you bring all the clean data that you know is a good behavior, and you start a new autoencoder. Input that data, compress it, reconstruct, and you finish when your training is perfect. So now I have a model that gets the good data perfectly reconstructed. Now, this model is deployed, and every time data comes, the model, this is reconstruction error, right? And this is time. This is the error, reconstruction error. Models error will go high if it's a bad data, if it's data that hasn't seen. When it's an abnormal data, the reconstruction error is going to be much higher than the other ones. So you basically define a threshold. For example, you say if the reconstruction error was above the threshold, that's the abnormal. That's, for example, that deviation, or that's a attack, or that's something suspicious on the network. Right? That's how we use autoencoder for anomaly detection or novelty detection. Okay. So there are different basic reasons that you can use autoencoder, but in general, there are simple networks that they are unsupervised, and mainly we use it for some sort of like a dimensional reduction. It's common actually for the last two, depending on the domain, it's common, but it's really common for dimensional reduction, especially if you don't want to make weird assumptions about your data, like PCA, for example. So autoencoder is something that you can apply to your data set. And the learning of this autoencoder is exactly the same thing that we have forward, backward. Nothing is changing. Depending on how many layers you put, you do a forward, calculate the error, gradient, traverse, backward. When you reach to the back, update and repeat the same. Okay, so that's the learning is the same. Any question on that? Good. Okay, so we are going to start with convolutional neural networks, or CNN. Okay. So convolutional neural network is a type of neural network, basically neural network type, which we mainly use it for image processing, video processing. We can also use it for NLP, because we have convolutional one dimension, 1D. We have convolution 1D, 2D, 3D. So we can use it for NLP also, but it mainly was developed for working with image data, you know. Now, so far, everything that so far we saw, we kind of were, so in feed-forward neural network and this autoencoder so far, the input data was still a vector. X was one vector. And every algorithm that we solved up to this point, we were input data in classical machine learning was a vector. But now, what if your input data, one example, is a matrix, like an image, for example, right? Image, you know, it could be black and white, could be gray scale, could be like a color. So if it's color, for example, we know it has RGB, 3 channels, right? RGB, right? So every image has 3 channels, and every channel is a matrix of numbers, right? So it's also called Euclidean space, basically. So the image pixels vary between 0 to 255. Okay, so minimum 0, maximum 255, depending on the, you know, the brightness and the darkness of basically color. Now, the idea here is that, okay, if I have this image, how could I learn from it to make a task, classification, regression, whatever, right? Think about humans. When we are looking at an image, quickly you can basically analyze it, see what is in it, make a decision, classification, or whatever, right? So our goal here is that how to do that. Before this convolutional model in classical machine learning, what we used to do was that we used to pick this image and convert it to one vector. It's called flattening. Okay, flattening means that means I will pick this first row pixel, I put it here, and I pick the second one, I append it to it, and so on and so on. I convert this image to a long vector, sometimes too long, basically, if the image is too large, and then I pass that to classical machine learning that we have seen so far, because it's just one vector. The problem with that is, think about an image. Like if you're looking at an image of anyone, it's like human, dog, cat. First, it's like the forehead. Imagine you pick the forehead, and then you pick the eyes, you put it after. And you're asking the image, well, what's in it, right? So it's going to be really difficult for the models to basically understand, right? It's possible, it's not that impossible. You will learn something because as by process you have enough data basically, but you learn only basically like it's kind of like you don't learn the contextual meaning of the image. Like if this comes by this, what meaning it has. Like you just learn exact like a pixel. Okay, this is going here, this is going to be here. It's like it doesn't have the contextual meaning behind it. So CNN, rather than doing those, our goal is that how could we pick the actual image and how could we basically process it, break it down into meaningful features, set of features. So convolutional neural networks, it's the types of neural network which is developed over a function called convolutional function. Convolutional function is a mathematical function, basically, right? So it's a mathematical function over two functions. So let's say I have it's a function over G and, for example, H, convolutional function. It's a mathematical function that you apply. Now, convolutional neural network, the way that it works, you're going to, before we say the talk, actually, before the way it works, let's talk about that, what we want to do. The goal in convolutional neural network is to learn the best basic features from the image. But how? By reducing the spatial dimension of the image and increasing the depth of the image. So the goal in convolutional neural network is that to reduce the original dimension, but to increase the depth. Okay, so that means we want to go from here, let's say, for example, to here. Where each of this, for example, could be a much smaller network, not 2 by 2, it could be much smaller. And the idea will be that each of these have learned something different about your data. Each of those we call those activation map, they are representing something unique about the data. So basically, rather than trying to look at this image and try to analyze all of it, we try to break it down into smaller pieces where each piece has learned something different. For example, one piece could learn what is the definition of brightness in the image. One piece has learned what is what's an edge. One piece learned what's a color. One piece learned what's a, parallel line. Each of those pieces are going to learn something about your data. Okay, and then you will bring this learning, because it's a much smaller learning, what is lengthier. At the last step, you're flattening it. So last step of a convolutional neural network is after I have that, I flatten it, convert it to a one vector again. Okay, because you need to do that. But when we do that flattening, now it's one long vector. Then all I need to do is to put one fully connected layer, one layer exactly like what we learned after the flatten, and then make a prediction. Okay, so you have learned everything up to this point. The learning is done here. In this part, in order to put those learnings together, because they are in a different form, it's not easy to basically process them. You put them in one flat line after each other. And then you just simply put one layer after, just some random weights to be able to adjust if something went wrong after flattening. So you're going to learn some weights here and then make a prediction, just one layer. So every convolutional neural network has the following structure. Whatever you do, at the end, you do a flatten, one fully connected, not necessarily one fully connected. You could put so many fully connected, depending on your choice. But it should be flattened, fully connected, prediction. Okay. Now, in order to go from here to here, Okay, we are going to use a concept, basically we say that is a convolution. So in order to do this convolutional function, this convolutional operation, basically the term also is called to convolve over the image, right? In order to do that operation, G, okay, is going to be your data. Okay, G is your data. And H is a function that you're going to basically apply over this data as another thing. It's going to call kernel. Okay. Now, kernel is going to be a square matrix. Okay, it's like a P by P, for example. Or let's call it. Right. Filter, sorry. Filter. It's going to be let's say F by F is going to be a square matrix. Now, the idea that behind this filter is that it's going to be a square matrix of weights. It's simply a square matrix that has some random weights. Not thinking it's not random weights, but let's say some random weights that we are going to learn those weights. Okay, so again, that's not the random weights. Depending on what you want to learn, actually, filters are going to be. If you want to learn, for example, like if you have something called identity filter, is a filter that has the it should be 3 by 3. That's it. It's that identity filter. Because everything that you multiply by this filter, we produce the same thing back again. It doesn't do anything. So different filters, they have a different values as weight over there. Okay. But the way that filter works is that it's a square matrix that has its own weights. For example, W1, W2, W3, W4, and you are going to pick this filter and convolve it over the image. Now, the idea of convolving over the image is if I let's say this is one image. Okay. Let's say this is supposed to be a square filter. This is a filter. And I want to convolve this over the image. So you basically bring this and you put it here. Okay. This first time when you put it here, it's like if it's supposed to be, for example, 2 by 2. Then all you need to do is that to multiply weight by exact same values. Every weight value, because it's a square, goes on it, right? Corresponding weight multiplied by corresponding pixel. Okay, and you do weighted sum. And you could also have a bias term plus the bias. So when you do that operation, the output of that is 1 square of number, some number. Because again, weights times this, weighted sum plus bias produce 1 number. Then the process comes by sliding this filter across the image. So from here, now I go here. This also produces 1, right? From here, I go here. This, for example, produce 1, right? It's supposed to be 2 by 2, so it's kind of becomes, this becomes 1, then this becomes 1, and this becomes 1, so 3. Then I go next page, next row. For example, this. And I go to the next one, this. So we slide this filter over this image with the goal of learning something different about this image. Filter is learning something different. And also it reduced the dimension of the data, right? So not always definitely this sliding will reduce the dimension. Depending on size of your filter, and also the sliding window that you use, we will talk about it, you might actually produce the same dimension. Right? If your filter is, for example, 2 by 2 and you move it one at a time, you're going to produce the same thing, right? So it depends on, but normally you will reduce the dimension. So now, so that's one thing, but my image had 3 channels. Okay, so I just did over 1 channel, not all of them. So that means filter has also a depth. Okay, depth of a filter is exactly the same as the depth of the input that you want to slide over. That means if I have 3 channels, each filter, this is 1 filter I'm talking about, not 3 filters. Each filter is a 3D matrix. And each dimension of that matrix is responsible to slide over 1 dimension of the data. Each of those, and those 3, they have different weights. You are going to learn different things, right? And then we are going to, one example is that we are going to simply, so now this is actually a 3D. I learned 3 of these, okay? 1 per dimension. Next thing, one thing you could do is that you could simply sum or average the values along the same axis. That means this 3, I will average them into 1 or sum those into 1, and then this 3, and then this 3, and this 3, this 3, this 3, this 3, this 3, this 3, right? Now, this at the end will become a 3 by 3. So filter, each dimension of a filter creates 1, but at the end you either average those or sum those, for example, into 1. This is called activation map. This learning that you learn based using the filter called activation map. Why activation map? Because filters, when you look at this example, filters have zeros and some numbers, like 1, for example. When you say activation map, every zero doesn't learn anything, right? The one that has a number, for example, is going to learn something. So it's kind of like this pixel always being activated. These are deactivated. The goal is that this filter, based on the value it has, is responsible for learning something. So the output is going to be a map of activated cells. So we call it an activation map. It's whatever we learned from that basically data that we have. Is this clear? All right, okay. So that's the filter. The next thing we're going to talk about is called a stride. Okay. A stride simply is like the definition of a stride is that, you know, when I move this filter, that's a stride. How much you're moving it? Are you moving it 1 cell at a time, 2 cells at a time? That means, for this example, just simply here, this is a stride of 1. I go from here to exactly here. If a stride is 2, I go from here to here. I jump. If a stride is 3, I go from here to here. A stride is that moving window. How, do you want to move it by 1, by 2, by 3, right? So a stride basically, the impact that it has is, if your stride is smaller, like 1, you're basically going to reproduce almost the same thing, because you always move by 1, right? If your stride becomes larger, the spatial dimension that you reproduce is going to be smaller. Depending on what stride you choose, your data, so if your data set is expensive and you want to force it to become a lower dimension, pick your stride larger, like 2, 3, 4. So probably, I don't know if someone uses 5 or something like that, but probably like 2, 3 is like really common. So, but if your stride is always 1, it's like basically you reduce the dimension by 1 technically. It's really like a smaller dimensionality reduction, a spatial reduction, right? So that's a stride, like the moving window size. Okay. The next thing we want to talk about is called padding. Okay. Now, let's say for this example, I have another dimension here. Okay. I have 5 dimension, original dimension, and I want to pick this like this because it's supposed to be 2 by 2, and I want to stride it by 1. Okay. So this is 1. I move it here. This is next. This is next. This is next. But when I go to this one, what is missing? You see? So I cannot do a stride on this one because I don't have data. So because of that scenario, you are missing some information, some data, normally at the edges of your image. So padding means that you're going to increase the spatial dimension by putting simply like zeros around it, for example. So that means I will bring here and I add 0, 0, 0, 0, 0, 0. Around the image, for example. It's called 0 padding. And then I stride. So 0 doesn't do anything, but it helps me to not lose information. Now, padding doesn't necessarily need to be 0 padding. We have average padding, we have max padding, mean padding. There's like different paddings that you can apply, okay? That means that if you do, for example, average padding, I will average these 2 values and I put it in the padding, for example. Or max padding, or rather than 0, you could also put 255 all around, right? Different paddings you can apply. But the idea of padding is that to basically to pad the data data by some values like this. That's the padding. All right, so we talked about the convolutional layer. We talked about this padding, and then now we're going to talk about the pooling layer. Pooling layer, it's a layer that it's kind of like the idea is similar to the convolutional layer. Remember the convolutional layer, we have this filter that we move it. In pooling layer, we also have a filter, okay? So we will have a square filter in pooling layer. However, there are no parameters here. So pooling layer, no learning. You are not learning anything in a pooling layer. No weights, no bias, nothing. The only benefit of pooling layer is that to help us to reduce the dimension of the data. It's a dimensional reduction layer, basically. How it works? So let's say your goal is that to have a large image to convolve over, and then now you have a more depth, but then your data is still too expensive. So what you do is that technically after every 2, 3, this is kind of like common. You can do after every also, but normally you do after 2, 3 convolutional layer, you put 1 pooling layer. And the way that pooling layer works is that you pick this one, same way that you apply the filter over the image, and you apply it over the activation map. Now, depending on the types of pooling layer that you use, let's say we use max pooling. Max pooling. So I have this data that has 1, 2, 3, 4, 5, 6, 13, 14, 15, 16. That's my activation map data. And it has different dimensions, okay, but we don't care about that. Now I want to apply a pooling layer, and my pooling layer is a max pooling. It has a 2 by 2 filter. And it has the same parameters. The stride and padding also exist in the pooling. Okay. So let's say I want to have a stride of 1 and no padding. Okay. So I'm going to pick this and go over this one and put it here. So because it says max pooling, when I put it here, that means you're going to select the maximum among those pixels, which is 6. So the output is going to be 1 squared is 6. Then I move it by a stride of 1. Next time I'm going to here. What's the max? 7. Next time is 8. Right? Then I go down here. 10, 11, 12, 13, 14, 15. Oh, 14, yeah. 14, 15, 16. So max pooling means that simply you go based on your filter size, you pick the maximum among those pixels. Why do we do something like this? Because when you're looking at adjacent pixels, they're kind of the same. Like if they're dark, it's dark, right? So when you pick the maximum among those, it's going to be that you pick the sharpest image, sharpest pixel, for example. So that's technically that's why we can do that. It's fine. So you could do average pooling, for example. You average those into 1. There are different pooling types also you can apply, but irrespective of what type of pooling you apply, the process is this. Okay. You also have kernel pooling, or for example, you could have your own kernel function. That means you have a function that gets these 4 values, some mathematical operation, and gives you another value. So that's also possible. So that becomes the pooling layer, and it gets the data. Now the idea would be that the way that convolution works, you have input layer, convolution, for example. Pooling, convolution, pooling, convolution, pooling. And there's always a stack them like that. After a couple of convolution, you do some sort of pooling layers to be sure that, because convolution, you normally stride small, so you might not reduce the spatial dimension that drastic, but you want to reduce it, so you do pooling to be sure that, okay, I'm reducing the dimension as well. Okay. We are not learning anything because there's no way. That means when you do backpropagation, there's nothing here to update. You just pass it. There's nothing here. It's just the problem here is that you lose some information. That's correct. But it's just a cost that we basically pay in order to be able to process this type of data. Okay, so now one thing that's really important is to understand that how the dimension basically work in convolutional process. So we can calculate, we can estimate the dimension of the output of the layers. So let's assume you have an input, which is W is the width, height, and D is the dimension of the data, the depth of the data. And you want to do a convolutional process. In order to do convolution, you need 4 parameters. K is your filters. How many filters you want to apply? So each convolutional network, convolutional layer doesn't have just one filter. It has a series of filters. Okay, that's important to remember because you're not just learning, convolution is an expensive layer. You're not just going to learn one filter. You're actually going to learn, I don't know, 256, 512 filters, 64, something like that. Okay. So K becomes number of filters, different filters, number of unique filters, basically. Okay. F is each filter is a square, F by F, right? So F is the dimension of the filter, which is F by F is filter dimension. Okay. S is the stride, and P is the padding, for example. Now, in order to detect what is the dimension of the output of this convolutional layer, what's the, with activation that map that we're generating, I say that you're reducing, especially increasing the depth. What's the dimension of that? You're going to use this formula. The new width is going to be coming from this formula. Previous width minus F, filter size, plus 2P. P is the padding, how much padding you add, 1 padding, 2 padding, right? Divided by S, which is the stride, at the end, minus 1. Okay, so that's going to be the new width size. And for the new height also, it's going to be the same thing, basically, because filter also is, again, is a square, so height and width are going to be the same. Right, that should be plus 1. That means plus 1. So now the output dimension is going to be W prime times H primes times D prime. But we want to talk about what is D prime first. Now think about it. Filter, I said a filter is a square matrix, right? Each filter is in a square matrix. But I also say that filter also has depth, right? And the depth of the filter comes from the data that it needs to slide over. So here, input data has depth of 1, D1, correct? So that means every filter that I have is going to be F by F by D1, exact same depth, every filter. Okay. However, when the output of this you want to calculate, how does the output work? Think about the process. Every filter, you convolve it over the image and it learns an activation map, right? Then you average all those activation maps for one filter or sum those into one activation map, correct? So how many filters in total we have? How many activation map we will generate? Okay, so the output dimension, what is D prime? The new depth is going to be K because you have K filters. Every filter learns something about the data. So always the output of convolutional layer, the depth is going to be exactly equal how many filters you use. Because every filter learns something. So again, let's refresh this. You have K filters. Every filter has the following shape. So you have K of this. K filters, basically. Exact same shape. F by D1. Values, the values in the kernels are going to be, the filters are going to be different. Right? But they're exact same shape. One filter at a time, you pick the filter and you convolve it over the input data. Okay? So a filter has D dimension. That means that matrix is not one matrix, it's D matrices. Every dimension of the filter is going to slide over the corresponding dimension of the image. First one goes R, And after it goes over R, it produces this one. Second one goes on G and produces this one. And third one goes on B and produces this one. Now you have three. We don't need all three. So what we will do is that we combine them together, either by sum or average, right? Or other operations. You just need to make them into one. So you pick these three and you return just one. Does it make sense? So every filter will produce now just one. The size of that one, what is that size, comes from this. W prime times H prime is one dimension. There's no depth in it. Depth is one. Now, or let's get it here, one. Now, how many filters I have? K. How many of those I will create? K. So in total, when you put all of those on top of each other now, how many you have? W prime dot H dot D prime, which D prime is K. So that's how convolutional network works. You get the data, you start reducing the spatial dimension and decreasing the depth by using the filters. The more filter you use, the more depth you get. Right? But the goal is that every one of those filters are going to learn something about that image, that they're responsible for some learning. By doing so, rather than having a large email, I have a stack of really small, like not really, a small basically, it depends on the problem. Could be really small, could be a small activation maps, where each activation maps has learned something about the data. Then I will pick all of those and flattening those into one, this is at the end of the layer, into one long vector, and do one fully connected layer and make a prediction. Or two fully connected, or three, depends on again your problem. And that's convolutional neural network. The whole idea of convolutional neural network is this process of convolving over the image. Which convolving, again, this comes from convolutional function, which is a function over two functions, combination of two functions. So here, current filter is a function, and the activation map is also a function. So you convolving these two together, and it produces another data for you. You keep repeating this process until you have, you think you got to the point that you have learned enough. Then you stop with convolution, flatten, fully connected prediction. Is that clear? Sorry, your question.
How are you defining the
Find the weights for filter. So if you develop your own, let's say I don't know anything about it, then you can just do it randomly. But they also, we already have three defined weights, filters that we know. We know a filter for edge. We know a filter for identity. For example, that's filter for identity. We have exactly filter that is responsible for finding sharp edges. Like you can use exactly down filters, but you want to learn more, so you need to also have these weights to be adjusted by themselves. So we random filters basically, and you just learn them through the process. They are going to be responsible for learning something on the data. Questions? Is that clear? All right. I try to dense this as as much as possible. There's a lot, but that's the whole idea. It gives you some idea to start with. Okay. Now let's talk about something else. So we're almost done. Don't worry. There's no point. You're already here, so 10 minutes more than this, the last class. So let's finish the learning, and then you can. What's the point of imagine you are learning a model and then your model is running, you're tired, I'm stopping it. You need to allow it to converge, okay? So now, couple of things we want to talk about is that one is the optimization. We want to talk about this optimization. When you develop a neural network, you need to choose what you want to use. I want to use gradients, I want to use stochastic gradients, and there are so many algorithms out there, ADAM, NADAM, ARMS prop, LFS, PG. There's so many algorithms that they're all focusing on different things, right? There are a couple of them that I want to talk about, and it's just I think one of them is mainly is really focused for me here is that the idea of all of this optimization techniques are kind of the same. The goal is that we want to go toward the minimum, right? Or maximum, depending on what you're solving. But we want to speed up that process. That process is going to be lengthy and slow, so we want to speed up. Now, you already have seen gradient descent, you haven't seen stochastic gradient descent, which fasten the process. Now, we want to talk about something called stochastic gradient descent with momentum. Okay. So, the idea behind this momentum and stochastic gradient descent is that we are it's kind of like a physics-based algorithm that we're using. Let me write down the formula first. Okay. So one of them here is called stochastic gradient descent with momentum. And I just want to give you some idea that when you want to use a different optimization, what you want to focus on. So one idea here is that there are two dimensions, W1 and W2. Okay. Your goal is to reach to this minimum. And now imagine this is the process that you are currently doing. Right? Until if you get to that point. Now we want to say, okay, if I'm looking at this trajectory of my movement in order to get to that minimum point, is there a way to optimize that? Do I need to actually do so many fluctuations to get that point, right? Or could I basically optimize that process? You also already have seen Newton technique, right? I think some of your friends also was asking, they're using it in their project. So we know in Newton method, which basically we say that W becomes the W minus learning rate times gradient with respect to W times second order gradient with respect to W inverse. Newton technique. The first part, this part, is when it's basically gives you the direction of movement, right? You know, we already know the gradient gives you the direction of movement. Go to the left, go to the right, right? The second order derivation here that we get is called curvature. Curvature. Now, what is a curvature? This is a line, correct? Curvature is basically tells you the degree by which you need to extend this line in order to convert to a flat line. That's a definition of curvature for a line. By degree by which this line is far from being a flat line. So this tells you the direction of movement. When you multiply it by the knowledge learned from the curvature tells you that, okay, we know you need to go to the right. Direction is correct. But you're really going up. You're missing this much to be a flat line. That's what the curvature does. So it helps you, if you are going this process, it helps you to make it faster. Because it tells you that, hey, I know your direction is correct to the right, for example, but you're missing by this much to become a flat line, or this much to be a correct pass toward your goal. So take this much more. That's why in Newton method we have this second order derivation, curvature. Okay. Now, when we go into stochastic gradient descent with momentum on the other end, momentum, as the term comes, we want to introduce some physics-based ideas like a speed. How could we speed up the process? In order to do so, we introduce V, velocity, like velocity of movement. So think about here. I want to go from here to here. Rather than going all of this, what if along one of this direction, W1 or W2, for example, what if I take more steps, like a longer steps in this direction, like that? So on W1, what if I take a bigger jumps? Like using some speed, velocity. So in order to do so, we define this VG, which is speed, again, velocity. Velocity comes from the previous velocity times eta, which is a momentum. This is the momentum value. Momentum is, for example, is 0.9. You pick it's a hyperparameter. So whatever the previous value time multiplied by 0.9 minus learning rate times the gradient, right? So that becomes your velocity. You bring the velocity and add it to your W, and that becomes your update. But what does that tell you? That tells you that, okay, we know the direction is correct. We know that you need to go to this direction, right? But from the previous step, we also learned that the velocity, the speed should be this much. It should go that fast. You multiply it by some momentum, either reduce it, for example, by a small portion, and then take the step. That becomes your update. Using that update, you're going to update the W's that you have. Okay. Now, what is the impact of that? So I want you to look at here what we have. That is a 3D cost function. See, that's 3D cost function. The minimum is here. Also, probably you could do that if that's a minimum, just like this, for example. But you want to go down. The stochastic gradients and momentum, nag, ADA grad, ADA delta, RMS prop. There are different algorithms out there. But look at how the trajectory and the speed. For example, starting with ADA delta, you will see that how quickly it will go down. Right, the yellow. Then blue and dark, which is RMS prop and ADA grad, they are first going correct direction, but they're slow, right? Momentum, it first fluctuating a bit, but then it will surpass the other two, right? So it's really important for you to understand that when you work with this type of algorithms, they optimize for different things and they help your learning process. So if your model is slow, try different optimization algorithms. They're already pre-built, you don't need to build. If you work with TensorFlow or Python, you just need to change the import, use different optimization, and they help you with getting out of the local problem or getting a better answer or faster convergence. So try and error to pick different optimization and see how, basically what's the impact it has on the learning. And the last thing is that to see how the convolutional model works. So that's one idea. So you pick any image and you see we start to reducing the spatial dimension and increasing the depth as we go, right? And those squares that you see, those are the filters. Filter goes over there and produces that. That's a filter, gives that. This is a filter, gives that. And you keep doing that until you reach to this long, small, like a smaller spatial dimension, longer length, depth. And then you can flatten that. You basically could put a couple of, for example, fully connected layers and make a prediction. So this task is the classification part after the flatten. It's classification. Before that is feature learning. So convolutional neural network is a feature learning. You learn features on the data by convolving over them. The goal is that you learn all different activations. And then you do some task on it. Okay? So this is how basically also there should be one interesting This is the activation map coming out. And it's actually, it's also the video you see, this region that is colored is what the filter is learning. So you can basically, every layers of neural network convolution will produce another image, right? You can visualize them, and that way you can see every layer, what did you learn? So this, if you're looking at the image, you'll see that at every filter, you are learning something different from the image. So every filter is responsible for learning something, and then that way, basically, you combine all of those, and you have basically the learning that you need. Okay, so I definitely, for those of you that are interested into neural network, I definitely recommend you two things. Take the